Oh, the physicists agree on the physics, they just don't agree on what the physical world is like. I mean, that doesn't make any sense. That's what physics is about. It's about what the physical world is like. If you have a disagreement about what there is in the physical world, that is a disagreement about physics.
Hello, my geeslings. It is Mother Goose Robinson Earhart here with the introduction to Robinson's podcast, number 67. And this episode, as I say occasionally, is an absolute banger. This is a banger for the ages. This episode is with David Albert and Tim Maudlin, two of the world's leading philosophers of physics, or as they would put it, they work in the foundations of physics. So, David Albert is the Frederick E. Woodbridge Professor of Philosophy at Columbia University, and Tim is Professor of Philosophy at NYU. So David's a prior guest, episodes 23 and 30, and Tim was on episode 46, three of the best and most compelling episodes in the Robinson's podcast universe. And this episode is dedicated exclusively to the philosophical foundations of quantum theory. And David, incidentally, is the director of the Philosophical Foundations of Physics program at Columbia University. So we start off, this episode is pretty all encompassing, though it is far from exhaustive, obviously. But we start with the historical motivations of quantum theory, the sorts of lacunae in physics and experimentation that led to the development of the theory. And then we go into some of its most important concepts, superposition and measurement, before exploring what are referred to as interpretations of quantum mechanics, though Tim and David both objected to this, and that was a particularly interesting part of our conversation. And then we talk about other philosophical concerns related to quantum theory. So, backward causation, realism, determinism. And unfortunately, David had to leave after an hour and a half, but Tim and I continued for an extra half an hour, uh, just finishing up some lingering questions. And without any further ado, I hope you enjoy this conversation as much as I enjoyed having it with David and Tim. Just briefly, before we get into some of the philosophical concerns of quantum theory, for a bit of historical context, and I'm sure that the historical context could take days and days in itself, but just what were the sorts of anomalous phenomena or deficits in the physics at the time that motivated the development of quantum theory?
So Tim will have a lot to say about this too, and Tim has a really helpful first chapter of his book on quantum mechanics, specifying, I think there are 8 experiments you talk about.
Yeah, I take it this question's going about, if I understand it a little earlier, about what got people
yeah
up in this in the first place.
I think the most glaring thing is just the fact of the stability of atomic matter. It was, there were experimental investigations going on, which gave us some idea of the architecture of atoms, that you had these negatively charged electrons orbiting around positively charged nuclei, and it was an unambiguous prediction of classical Maxwellian electrodynamics, that if you had these charged particles accelerating constantly in their orbits around these nuclei, they would radiate away their energy by means of electromagnetic radiation, crash into the nucleus, the atom would cease to exist, the world as we know it would cease to exist. So there was this very, very glaring failure of and crisis in classical mechanics, just as a result of the stability of atomic matter.
Yeah, let me add. I mean, David's perfectly right. If we go back a little earlier, just to be a little complete. So you had Maxwellian electrodynamics at the end of the 19th century, which seemed to be very successful. Kind of the first thing it really failed on was the problem of black body radiation. So you just heat up a body. If you heat up steel, it goes from red to blue to white. And it turns out that that's just a function of the temperature. And so they tried to understand why bodies should radiate in a certain spectrum at different temperatures. And if you just naively tried to calculate that using the standard techniques of thermodynamics and Maxwellian electrodynamics, you got a disaster, the so-called ultraviolet catastrophe. That was the thing that worried Planck. That's late 19th century. Then there's this other effect called the photoelectric effect, which Einstein was worried about. He was the one who really kicked quantum theory off in 1905. And that's the exact details of how when you shine light on certain metals, you create currents. And the way that depends on the intensity and the frequency of the light was puzzling. And Einstein came up with a kind of quantum approach to that gave you the right predictions. And then, as David says, later on, you had the Bohr theory of the atom, and then you had these problems with weight radiation. So a lot of it is just electromagnetics plus thermodynamics at the time didn't work empirically.
And David, in quantum mechanics and experience, you write that everything puzzling about quantum mechanics comes from the notion of superposition. And that's what distinguishes our classical picture of the world from the quantum picture. And since this, I gather then, this concept of superposition is where so much of what we'll discuss today stems from, it seems like the right place to start. So just what is superposition and how does it differ from how we conventionally or in classical physics view the world?
Well, and Tim, please jump in on this wherever you feel it'll be helpful. Let's see. There's it's a sort of immediately unavoidable feature of the way the set of possible states of a physical system are represented in quantum mechanics. And it's also something that receives very direct sort of empirical confirmation in famous experiments like the double slit experiment and so on, that if given any two states which it's possible for a system to be in, that is, given, say, the state of an electron in which it's located at this point in space, and another state of that same electron in which it's located at this point in space, there will necessarily be a third possible state, or rather a whole infinite family of other possible states, which on the normal way of talking about things in quantum mechanics is neither the state of being located here, nor the state of being located there, nor in any familiar sense the state of being located in both places, nor the state of being located in neither of those places, but some previously unheard of kind of combination of being in those two conditions. This is the kind of possibility that's made vivid in in famous interference experiments, things like the double slit experiment or neutron interferometry experiments or something like that, where there's a certain condition in which an electron passes through a screen through a certain hole in the screen, another condition where it passes through another hole in the screen. Both of those are characterized by certain signature observable behaviors of the electron on the other side of the screen after it passes through the screen. And you can prepare these superpositions of those two states, which have characteristics neither of the one that passes through the left slit, nor of the one that passes through the right slit, nor in any straightforward sense of passing through both slits or neither slit, but is in some new kind of condition. I'm sure Tim has a lot he'll want to add to this.
Maybe I can approach this from a slightly different direction that makes it sound marginally less incomprehensible. There's the other thing that people talk about quantum mechanics is wave-particle duality, right? You often hear that. And the particular feature of superposition that David's talking about is a standard feature of waves. It's a standard feature, actually, of any system whose states are just described in a vector space and governed by certain linear laws. So imagine I have a water table, and I can send a wave from left to right, and I can send a wave from right to left. And I can also then send like half-size waves in both directions at the same time. And in the middle, they superpose. That is, the solution in the middle is just adding up with a certain weight. The solution I got of this one and the solution I got of that one. And then they pass through each other and continue on. That's just standard wave behavior. And it's easy to understand interference of the kind David mentioned in terms of waves. The problem is when you do these experiments with electrons, the actual electron always shows up in a particular spot, right? It doesn't get smeared out or spread out or anything. Mm-hmm. So in some sense, I mean, what John Bell said about this is you do these experiments and the little dots on the screen are really suggestive of particles, but the interference is really suggestive of waves. And with waves, you have superposition automatically. I don't know how to superpose a particle being here and a particle being here, because by definition, a particle is either one place or the other. You know, I don't know, it can't be 40% here and 60% here. I do know how to superpose waves. That's kind of trivial and very straightforward. But you had behavior that's suggestive of particles and behavior suggestive of waves. And people had a lot of trouble trying to put those together. Now, what Bell goes on to say is, why didn't it occur to him that one way to solve this is to say they're both particles and waves, and that the particle-like behavior is because there are particles and the wave-like behavior is because there are waves. And he's a little puzzled about why they were so puzzled, but historically that's what happened, right? But this is just to say it doesn't necessarily have to be so completely incomprehensible. There are kind of sort of pedestrian ways of dealing with these phenomena that don't involve anything quite as mind-blowing as breaking logic or anything like that.
Could you spell out for me how this relates to the difficulty of measurement, which I also take it to be something you identify, and I mean most people identify as a very big puzzle in quantum mechanics?
Well, again, I'm just channeling Bell here, but that's okay. I have nothing better to do. The puzzle about measurement is that in certain formulations of quantum mechanics, the concept of measurement appears in the fundamental statement of the theory. And Bell's objection was, that's the wrong kind. It would be like having the concept of pianos showing up in your basic statement of physics. You say, look, okay, there are pianos, but piano-ness is not the kind of thing that physics depends on. measurements are just, the experiments we call measurements are just physical experiments. They're physical interactions. Maybe you can characterize what makes them more or less measurement-like, but you shouldn't have to even define or discuss what a measurement is in stating the actual physical theory. That's just the wrong kind of thing to appear in the statement of a fundamental physical theory. So the problem isn't so much understanding measurement or defining measurement, but getting rid of it at a fundamental level. And again, we can do that. There are ways of doing that. And that, again, makes the theory seem much less mysterious.
Let me say a little more about that. And maybe we're sort of helpfully dividing ourselves up in this conversation between the way this looked puzzling to people early on, and which I've been sort of representing, and the way to demystify a lot of this in proposed solutions to the measurement problem, like Bohm's theory and so on, that Tim is alluding to. So let me say from this older perspective, look, this phenomenon of superposition initially looked very mysterious to people in a sort of deeply metaphysical way. Okay, it looked to them, and there are lots of ways of talking about this, and the history of this is very, very complicated, and one doesn't know quite what to attribute to who, or what to attribute to which version of who, and so on and so forth. But it looked to people early on like what was going on in the case of an electron, which is, say, in a superposition of being located at this point and being located at that point. Before this was demystified in a number of ways, one of which Tim alluded to by thinking both about a particle and a wave or something like that, it looked to people like what we were confronted with in a situation like that was a particle which we were used to thinking of, as Tim says, as the kind of thing which by definition is located at one or another point in space, okay? Which was behaving in ways, because of these interference effects and so on, which suggested to people that there could be circumstances in which, in fact, what was going on is that there failed to be a fact about where in space the electron was located. It isn't that it was located here, or that it was located there, or that it was located in both places, or that it was located in neither place, but rather it was in some sort of strange condition where asking about where it was located was something like asking about the marital status of the number 5, or asking about the weight in grams of Catholicism, or something like that. It represented some kind of radical category mistake, even to raise the question, okay? And that's strange enough, okay? If we take that kind of picture seriously, then what apparently happens when we make a measurement of the position of an electron in a condition like that, and it is an empirical fact that whenever we make such a measurement, we find the electron either over here or over there. It's never the case that we find some cloud, or things get woozy, or I suddenly get nauseous, or something like that, okay? We always find the electron either here or we find it there. notwithstanding the fact that we think we had good empirical reasons to suspect, reasons like the double slit experiment and so on, notwithstanding that we took ourselves to have good reason to suspect that right before we made this measurement, there wasn't even a fact about where the electron was located in space. Like I said, we took ourselves to have good reason to believe that before we made this measurement, asking where the electron was located in space was akin to asking about the marital status of the number 5. Okay, good. So then there's a puzzle. I mean, this is already puzzle enough, okay? But then there's a puzzle. How does the active measurement do that? Okay, the active measurement must be some very special occult kind of operation, okay, which has the power to transform situations in which there fails to be any fact at all about where the electron is, to situations where there somehow is now a fact about where the electron is, and moreover, that fact is reported to us, okay? So there was a big puzzle about how measurements manage to do tricks like that, okay? If you're looking at it that way, it becomes a little less surprising, though no less unsatisfactory, that a word like measurement might become very foregrounded in the way you talk, okay? And you can see how it might find its way into the fundamental axioms of this kind of theory, even though I completely agree with what Tim said, that if you step back for a minute, it's just crazy that you're going to find that word appearing in the fundamental axioms of your physical theory. So there was all sorts of what felt like really deep confusion about this. And the most extreme version of this confusion arises when it's demonstrated to you that if you do take this attitude towards superposition, if you take this attitude that being in a superposition of situation A and being in a superposition and situation B represents a third kind of situation in which it doesn't even make sense to ask whether you're in A and B. And if, with that interpretation of superposition in mind, you simply apply the quantum mechanical equations of motion to the act of measurement as if it was just another physical process, you get a result, which is that if you say measure the position of an electron, which is in a superposition of being here and here, with a measuring device whose pointer is going to swing to the left if the electron is detected at this point, and whose pointer is going to swing to the right if the electron is detected at the other point, what the equations of motion predict is that the pointer is going to end up being in a superposition of pointing to the right and pointing to the left. And indeed, if you then look at the pointer, your brain is going to go into a superposition of the brain state associated with seeing the pointer pointing to the left and the brain state of seeing the pointer pointing to the right. This is the formulation of the measurement problem due to Wigner, often referred to as the Wigner's friend story. So this, as it were, this virulent infection, okay, of being in superpositions spreads very quickly up the chain to macroscopic phenomena, if that's the way you treat these situations philosophically in the first place, and if you trust the equations of motion that we have from quantum mechanics. So there does seem to be a sort of radical, urgent, deep conceptual philosophical need to cut this off someplace, okay?
Yeah.
To guarantee that it's the case that there is a fact of the matter about where the pointer is pointing, and there is a fact of the matter about where you think the pointer is pointing, and so on and so forth. And that's that's how it could imaginably come to be the case that people are going to paint themselves into a corner where this word measurement ends up playing a role in the fundamental postulates of your theory that is not the role that you should rightly expect it to play.
Yeah, well, let me just make one more point, which is that we can connect this problem without even using the word measurement to the thing about the atom that David started with. And this is really what Schrodinger does. So again, there was a point where there was this kind of planetary model of the atom, right? You've got this heavy positively charged nucleus and these orbiting negatively charged electrons somehow. I mean, that's the picture we all see with these things. And they took that seriously, and they said, but how exactly do these things move? As David said, they ought to radiate, but even apart from that, you maybe just add some postulates that say they can't radiate, but then they have to jump between these orbitals. How do they jump, right? So they were breaking their heads over this. And the quantum description of the electron it doesn't give you an orbit or anything like that. It's kind of, as it were, smeared out. The electron orbitals, which they could calculate, have shapes. I mean, you've probably seen this, the s orbitals and the d orbitals, blah blah blah. And what happens is Schrodinger says, look, what's going on with the electron? And he says, well, maybe the electron is smeared out, right? Maybe we were just wrong to think about the electron as actually located in a particular place. Maybe it's literally smeared out in the way this suggests. He says this wonderful thing. He says, there's a difference between a shaky photograph and a snapshot of clouds and fog banks, right? That is, in the shaky photograph, it looks blurred, but that's epistemic blurring. It's not that the object was blurry. It's just that your information about it is incomplete. But there can be, as it were, blurry objects or sort of fuzzy objects like cloud banks. And you can take really sharp snapshots of them and they still look cloudy. And Schrodinger says, well, who knows? What do I know? It's microscopic. Maybe the electrons really are smeared out. But what he pointed out in his cat experiment is that, and this was a point that David's making, but it's not really about it being a measurement, it's that you can amplify that smeariness from microscopic up to macroscopic scale, okay? If you don't do something, if you just have the normal law, Schrodinger's equation, and you don't do anything, the smeariness can't be quarantined at microscopic scale, okay? It'll just go up and you'll get smeary cats.
Yeah.
And Schrodinger said, that's idiotic, okay? You've made a mistake at that point. And you got to do something about that. Now, I can say that without really mentioning measurement. Now, somebody might come in and say, well, it's going to be measurement ex machina, right? I'm going to allow measurements to somehow kill the smeariness down. But, you can state the problem without mentioning it.
But this is, by the way, this notion of measurement ex machina, I mean, this is a sorry history, but maybe a one worth knowing about. A natural impulse, you realize, okay, once we've painted ourselves into the corner that Tim and I have just been describing, something, this act of measurement, whatever it is going to have some very special status. It's going to have to come in and save us from this contagion that otherwise, because of the linearity of the equations of motion, just spreads uncontainably. And there's a natural temptation to look around for some other special kind of boundary that you could stipulate this contagion can't cross. And the latest, there among the speculations, and this is something else due to Wigner, is that that boundary was marked, for example, by the boundary between consciousness and mere materiality, or something like that. But the literature is filled for, I don't know, 50 years, with guys sitting in their bathtubs making pronouncements about where this boundary is located between microscopic and macroscopic, between indelible recordings and erasable recordings, between consciousness and unconsciousness. I remember with my own ears, and I remember, this is one of these moments you remember with this real sinking feeling, like maybe I got into the wrong business. Wigner being pressed about this and speculating that he thought it was likely that these measurement tricks could be performed by dogs, but probably not by mice. And you just said, this doesn't sound good, and I don't know, also what he has against mice is not
Yeah.
But people got themselves into terrible messes with this.
Tim, going back to smeary cats for a moment, and I gather you've already mentioned John Bell. I gather he's a big character in quantum non-locality and relativity.
Yeah.
And you've written a lot about this, but does John Bell's theory of local Beables relate to this problem of smeared cats?
In a way, yes, and in a way, no. In a sense, he's insisting there. I mean, there's this other problem about the wave function or the quantum state.
Yeah.
These are two separate problems.
Okay.
One problem is this tendency of it to be smeary, right? To kind of propagate like a wave and sort of spread out, which is why the wave can become wide enough to go through two slits at the same time and then later interfere. There's then a much deeper problem, which is that once you have, as it were, more than a one particle system, you can't even think of it as existing in three-dimensional physical space at all. It's not what Bell called a local Beable in three-dimensional space. And then, then you can be even more challenged to understand what it is. Now, what Bell, when he's talking about local Beables, he says, look, at the end of the day, you have to somehow connect your physical theory up to everyday experience, up to the lived world, if you will, or the manifest image, as we say. And certainly one way to do that, and the way he discussed, is to say part of the physics should be this local stuff in regular old three-dimensional space that's localized, and that you can make tables and chairs and cats and dogs and mice out of in recognizable cat-shaped, mice-shaped forms that move around in recognizable feline and muscine ways. Now, those could be particles, they could be more field-like or wave-like things, but localized wave-like things. So Bell's point, and David is going to disagree with this, and this is, if you want us to fight, this is where we'll put the gloves on. David's view, if I would put it this way, is he does believe there have to be local Beables. Actually, he sort of thinks all the Beables do have to be local, but not in familiar three-dimensional space, right? He's willing to pump the fundamental physical space up to a rather high dimensionality in order to have only local Beables in it. Whereas I'm happy, and I think Bell was happy, we want to keep our space down to regular 3 dimensions, at least at macroscopic scale, and put some local stuff in that corresponds to tables and chairs in a much more straightforward way than what David wants to do. I don't think I just said anything false. So, I mean, there's a weird paradox here, which is that in some sense, David has taken the demand for local Beables so deeply to heart that he's willing to do something much more radical than I'm willing to do. I'm willing to accept some non-local Beables, but at least also some local Beables in terms of which I understand the everyday world.
Yeah. Well, David, you're welcome to voice the dissenting opinion if you'd like.
It's a long story here. I'm not sure Tim may understand my deep psychological motivations better than I do, which happens.
Pushing and pulling.
You
want things to push and pull on each other, right?
To some extent, that makes more intuitive sense to me. It's also just a matter. I mean, this goes back to. There's a long story here. I've just finished writing a book that presents this somewhat differently than I used to present it. But the very flat-footed story is if you say, you ask a question like, what is to quantum mechanics? This is also going to depend a lot on how one solves the measurement problem. We've mentioned one way of solving the measurement problem, Bohmian mechanics here. There are other ways of solving the measurement problem on the table that Tim was briefly alluding to a minute ago, where it's not really it's not really the case that what you end up with is both a wave and a particle. There are ways of doing it which, if we were to continue in this language, we would say there's just a wave, but the wave doesn't behave in quite the way that the Schrodinger equation demands it to, so on and so forth. If you take a theory like that, for example, and you ask yourself, what is to this theory as particles are to Newtonian mechanics? Or what is to this theory as charged particles and electromagnetic fields are to Maxwellian electrodynamics? Or to put it a third way, what are the equations of motion of this theory, the equations of the motion of, okay? If you approach it in this very flat-footed way, the answer that drops right out is, oh, the wave function. The answer to all those 3 questions is the wave function. That's what the equations of motion of the theory are, the equations of the motion of, so on and so forth. And if you start from that, okay, then there's going to be a temptation to say, aha, so that at least suggests I ought to be taking the wave function as the fundamental, concrete, ontologically serious object in quantum mechanics, in the way that I take particles in Newtonian mechanics or particles in electromagnetic fields in Maxwellian electrodynamics or something like that. Then you ask, gee, but what would that commit me to? Well, as Tim just said, this wave function isn't something that lives in the mathematical sense in a 3-dimensional space. Maybe that means we ought to think about whether there's a way of taking this much higher dimensional space seriously. That's, of course, immediately going to raise a question. So what's the deal with the fact that the world presents itself to us as three-dimensional, that we talk about it as three-dimensional? Can we find an explanation of that that's compatible with this story that I described a few minutes ago about what we want to say is the fundamental ontological object? You pursue this, and you find that that there is a way to tell this story, and so on and so forth. So one way to motivate it is, as Tim said, to say, I'm going to look for any space I can find such that in that space all the Beables are local. I don't think that's the only way to motivate this kind of view. There are a bunch of them. I don't think any of them, by the way, are decisive. I don't. A lot of dust is going to have to settle before before people feel comfortable, if that ever happens, saying, yeah, it looks like this or that is the best view of the metaphysics of quantum mechanics. But yeah, if the question is, can I imagine motivations for pulling away from the three-dimensional view that Tim was talking about? Yeah, I can.
Yeah, let me also just add a terminological point, because people who don't know this, I think, can easily get confused. And okay, what's done is done, and I guess can't be undone. There's a trademark phrase called wave function realism that has been adopted to refer to the view that David is talking about, which is committed to the fundamentality of this very high dimensional. If you say, is there any physical space, fundamental physical space? Someone says yes, and furthermore, it's this very, very high dimensional space. It's not three-dimensional. In the normal sense of, quote, wave function realism that any philosopher would understand that phrase, if you poke me and say, are you a wave function realist? I'll say, sure, I am. I think the wave function describes a real objectively existing physical item. I don't think it has anything epistemic about it. I don't think it's a description of our knowledge or our beliefs or anything like that. There's normally a distinction made between something being merely epistemic and being ontic. I believe the wave function, the mathematical wave function, describes a real ontic item. But I don't believe it is there is this high dimensional space, physical space it lives in some sense. So by the trademark meaning of the term, I'm not a wave function realist, but by the intuitive meaning of the term, I sure am. I just want for people to understand that if they start reading around about wave function realism, it's very easy to get confused because of the natural, conversational implications of that term. Now, Alyssa Ney has recently published a book defending, or at least investigating, I should say, somewhat defending and somewhat just investigating the trademark view. And in the book, when you ask, but what are the virtues of this view, or why should I be attracted to it? At least the answer she gives is because it gives me a picture that is local and separable. So these are just, again, kind of words that go together with the space, the fundamental space. And we agree, if you want something local and separable, you're sort of forced in that direction. So this is, I think, part of that was the motivation I was trying to attribute to David psychologically, if that's of any help for people who are reading around here.
Taking a step back for a moment before we get back into some specifics, much of the philosophy of quantum mechanics as I understand it, which is granted not very well, stems from a sort of tension, I guess, between the formalism of quantum mechanics on the one hand, and then how we interpret it on the other. And I wonder, just for my own understanding, if I'm right here, that is this at all analogous to some of the central debates in the philosophy of mathematics, where everyone, I mean, for the most part, though there are notable exceptions, agrees about the math itself, uh, but there is little agreement, though. I mean, Tim might disagree with me here, on just how we should conceive of the world in order that we can take the statements of mathematics to be true. So maybe what I'm asking is, in the case of quantum theory, do the physicists agree on the physics itself, and it is just how we're supposed to conceive of the world that they don't agree on? I see David.
I'm sorry. You're using the standard terminology, and what you said is not at all idiosyncratic, but man, do I hate it, right? I mean, it's like, oh, the physicists agree on the physics, they just don't agree on what the physical world is like. I mean, that doesn't make any sense. That's what physics is about. It's about what the physical world is like. If you have a disagreement about what there is in the physical world, that is a disagreement about physics.
I completely agree with Tim here, but one can say something even stronger than that. It isn't as if there's agreement on what the right mathematical formalism is to use, or what the empirical predictions of the theory are. So in that way, it's really different from the case of philosophy of mathematics. There are various theories on the table we referred to here, various different ways of solving the measurement problem. Bohm's theory, the GRW theory, maybe Everett theories, although I think both Tim and I are worried about whether that turns out to be coherent at the end of the day. But focus on Bohm's theory and the GRW theory. These theories make different empirical predictions. Their mathematical formalisms are very different. It is certainly not a case of, you're presented with a finished mathematical formalism and your job is to interpret it, okay? Whatever that means. These are different mathematical formalisms. They make different empirical predictions. Unfortunately, the situations in which they make different empirical predictions are not at the moment accessible to us experimentally. That's essentially a technological problem. But these are, first of all, for the reason Tim said, but for even more flat-footed reasons than that, we're talking about different claims about the world. There's some sense in which, much more than in the philosophy of mathematics, what's going on here, what's being discussed here, especially with regard to the measurement problem, is a scientific problem. It ended up in philosophy departments, or at least a lot of it ended up in philosophy departments because of weird historical circumstances that drove it out of physics departments, during a certain period of the 20th century. But this is a large part of the contribution, it seems to me, that philosophers made to the discussion of the measurement problem, was arguing that it was not a philosophical problem, that it's a scientific problem, okay? It turned out that was something that for various historical reasons, and also for reasons of how they were trained and what their expertise is, that philosophers were in a position to say clearly, no, let me tell you what this is. This is a scientific problem. It needs to be solved by ordinary scientific means, by writing down new equations of motion, which make different empirical predictions, which then have to be tested.
Yeah.
So no, it's very different.
I completely agree with that, and now to be even slightly more pointlessly aggressive here, let me just say,
before you're more pointlessly aggressive, which is totally fine. I hope that my question was at least reasonable.
Yes,
well,
no, your question is helpful.
Okay, good.
Yeah, but
it's allowing us to make something clear that I think it's important to make clear.
Perfect.
Right, but let me just push back a little bit about how relatively happy the mathematicians are. Look, there are disputes in mathematics, like about the axiom of choice or about the continuum hypothesis or whatever. And I would say, look, if you're like me, you're going to say they're correct and incorrect answers to whether the axiom of choice, or certainly an incorrect or incorrect answer about whether the continuum hypothesis is true. And if you decide to adopt a mathematical system that makes the wrong choice for an axiom, then it's kind of a worthless system, because yeah, you can derive a bunch of stuff from it, but you're deriving it from a false axiom, so who cares, right? I mean, you say, well, gee, if I put this large cardinal axiom in, I can derive blah, blah, blah. And I say, well, why should I care if the large cardinal axiom is false? Now, you can take a view of mathematics where there's no facts about these things. I don't think it's very defensible. But I don't think even mathematics qua mathematics is in quite the happy situation that everybody agrees about the math, right? No, I mean, I think, intuitionists didn't agree about the math. They didn't agree about what was a theorem. They didn't agree about what you could trust because of the methods used to derive it. And I think those are serious mathematical questions.
Mm-hmm. So I'd like to shift back to the specifics, and in particular, one of the central topics in the philosophy of quantum mechanics, again, I think, is the Einstein-Podoksky-Rosen argument, the EPR argument. And I guess, first of all, what is that argument? And again, Tim, since this is a major subject of quantum non-locality and relativity, how does this relate to John Bell?
So look, the story here is historically pretty simple, but it has been massively mistold and misunderstood. Einstein is known, even though he essentially invented quantum mechanics in 1905. I would give him more credit than Planck, of hating the quantum mechanics that was developed in the late 20s by Heisenberg and Bohr and Schrodinger, and the matrix mechanics and the wave mechanics. He hated it. He hated it, fought against it his entire life. And his main objection to it was not that it was indeterministic. His main objection to it was not that God plays dice with the universe, which is what you're told. His main objection from the beginning was non-locality, that if you took the theory seriously as a physical theory in the way people like Bohr were asking you to take it, that something that happens at one place would cause a change in the physical state of the universe arbitrarily far away instantaneously. That change in the standard presentation is mediated through what's called the collapse of the wave function. Okay? He hated that. That's a kind of and furthermore, he saw it kind of had to be instantaneous. It had to go faster than light, but it also just seems spooky. This is what he calls spooky action at a distance. Mm-hmm. And he couldn't get a lot of traction getting people upset about that, because they were so fuzzy about what they were saying, and half the time it was ontological and half the time it was epistemic, and sometimes it's like you're having a physical effect and sometimes you're just doing Bayesian updating, and nobody knew what the hell was going on. And the EPR argument was just to make as sharp as possible that if you accepted the completeness of the quantum mechanical wave function, that is, that all the physical facts about a system are encoded one way or another in the quantum mechanical wave function, you would be committed to this spooky action at a distance. Now, Einstein, they didn't quite write it that way. He just thought the spooky action at a distance was so idiotic that nobody would accept that. But then you put it like it's modus ponens, modus tollens. To avoid that, you just have to admit there's more than the wave function. You have to admit that quantum mechanics is incomplete. That's the title of the paper. Is quantum mechanical description of reality complete? And that argument was arguing, no, it isn't. But it was presupposing that you don't want this spooky action at a distance. That still didn't move people because they kind of denied there was this spooky action at a distance, but they never made anything clear. You can't understand Bohr's response and so on. Now, what happens is in 1952, David Bohm writes a paper which revives a theory that had already been produced by Louis de Broglie back in 1926, right at the beginning. And it's a nice, clear theory. You understand what's going on, and it's so clear you can see the non-locality. Just, it's in your face, right? It's really in your face. And Bell wondered, could he get rid of it? Because he liked the theory because it was clear, it was mathematical, it didn't invoke measurement or anything like that. Everything's just in the math. But it had this non-locality, and then Bell asked himself, well, I wonder if you can get rid of it and keep all the same predictions. And what his theorem shows is that you can't. That the non-locality is playing a role in producing the empirical predictions such that you can't even get the same empirical predictions without some form of non-locality. Now, Einstein didn't live long enough to see that. If he had, I like to think he would have seen Bell's point and he would have stopped being so upset about non-locality because he just would have shrugged his shoulders and said, well, I'm stuck with it. I think that's the correct, right? The correct reaction. And I think Einstein would have had it. So the EPR paper plays an interesting role. It's central. It's central to the chain of thought that led to Bell. Okay, but it was not arguing for what Bell's arguing. It was arguing for the opposite of what Bell's theorem proves. Right? Bell's kind of proving you must have non-locality. EPR was arguing if you want to avoid non-locality, you must have more than quantum mechanics now has. And Bell sort of says, even if you add some more, you're not going to get rid of the non-locality, right? It's an ineliminable part of the thing. So I'm not sure if that. It's very, you have to appreciate the EPR argument to understand what Bell was doing. And in the beginning of Bell's paper, he mentions EPR. It's actually called On the Einstein-Podoksky-Rosen Paradox. And he assumes the reader understands as far as they got. That turns out to be way optimistic because most people who read the paper didn't understand it. And so then you had another decades of mess trying to get people to understand what Bell did.
So, returning to my question that earned the spirited response, I gather that I'm incorrect about the relationship between the philosophy of physics and the physics itself. And just what then is an interpretation of quantum mechanics?
So this is, all right, let me come back to that. I hate the word interpretation.
Okay.
Right? I think it's just misleading. I actually don't like philosophy of physics. If people ask me what I do, I say I do foundations of physics. Okay? And if they ask me, why aren't you in a physics department? I'd say, well, in an ideal world, I could be. It's a sociological fact. David should be, right? He is a PhD in theoretical physics. He belongs in a certain sense in a physics department, but they just decided they don't want to do that bit of physics. And I don't like the word interpretation because it really underplays what's at stake. What's at stake is these are just different theories. They largely make, but not entirely, as David points out, the same predictions. So they're hard to distinguish empirically. But they're just different physical accounts of the world. Don't call them different interpretations. They're not. They're different theories that happen to make pretty close sets of predictions.
I mean, one can go. So first of all, I agree with Tim completely about the terminology. I also describe myself as doing foundations of physics rather than philosophy of physics. And I think, I mean, this would require some historical and sociological research, but it feels a lot like the word interpretation was another of the defenses that physics erected in order to a way of minimizing what's at stake in this problem, and as a way of excusing themselves as physicists for not attending to this problem. This is a different kind of problem. This is a different category of problem. This isn't a scientific problem. This is a problem of interpretation of an existing scientific formalism. Yeah, I think it's an important point to make, and it's a point, and this is why your question is useful and helpful, giving us an opportunity to emphasize this point. I don't think that's what's going on. I think this area of work is is a place where, well, like I don't even want to say that. This is, a big part of the contribution of philosophical discussion on this topic was the business of making it clear that this was a scientific problem.
Well, no, that is really helpful. So I'm glad that I've asked these questions. It's really good. Now I'm gonna avoid using the dreaded I word, and instead I will ask then, what was the Copenhagen theory? Was it?
Well, no. Okay, so the conversation has taken a deeply ironic
Yes.
at this point. Copenhagen is not a theory, okay? I don't know what it's roughly as much of a set of claims about the way the world is as sort of, the ravings of the oracle at Delphi are a set of claims about the way the world is. I guess Tim and I have slightly different impressions here about what Bohr was up to, although it's really hard to have any clear impression of what Bohr was up to. But I guess I tend to see Bohr as a very militant instrumentalist about this theory, that there are all kinds of statements that you can find, for example, in Bohr's response to EPR, that are supposed to be admonishing the reader against taking quantum mechanics as some kind of account of what's actually going on in the world. Its aims, as I read Bohr, and once again, reading Bohr is a really hard thing to do, but as I read Bohr, or to the extent that I can cobble together anything that looks like a consistent view out of what Bohr says, he's severely limiting the aspirations of physics to making correct predictions about how experiments are going to come out, and admonishing the reader not to understand this as some kind of a realistic account of what's going on, as it were, under the table or in between the experiments, or anything like that, and a warning that thinking like that is only going to lead to paradox and madness, and so on and so forth. So no, Copenhagen is, what I think Tim and I will agree about this. Whatever Copenhagen is, it's not the name of a theory. Okay. It's the name of a bunch of warnings and slogans and precepts and about what you're supposed to do with this quantum mechanical formalism.
Yeah, I mean, look, we David and I absolutely agree. What came out of and sometimes it's even just called the Copenhagen spirit, right? Which tells you how vague it is.
Yeah.
Doesn't amount to a physical theory, which should contain clear statements about what the theory postulates to exist and how that, whatever it exists, behaves. I mean, I will say just historically, I don't think of Bohr as a kind of, all I care about is the predictions kind of guy, right? That sort of, and there are physicists who are like that, right? They say, look, I just want a predictive mechanism, and beyond that, I don't care, or don't ask, or it's not part of physics. I mean, that position, kind of instrumentalist position, has been taken. Certainly, when Copernicus's book was originally published, there was this preface by Osiander trying to keep Copernicus out of trouble, basically saying, look, I'm not literally saying that the Earth rotates on its axis and orbits the sun, but gee, you can calculate more easily if you pretend it does, and it's just an instrument for making calculations. That I don't think is Bohr's view. That's easy to describe, and there are some physicists who take that approach. Let me just give you a taste of some of the things Bohr, I think, does say, that maybe will give you a sense of. I mean, he seemed to think he had a very, very deep philosophy, and he was getting very deep insights out of it. Whereas this other thing is much more pragmatic, and you can say it in 5 sentences. So Newton would say of a particle, at every given moment, it has a definite position and it has a definite momentum, right? It's just somewhere, and it's going at some velocity. It has some mass. There's always a fact at every moment about both of those items. And Bohr would say something like, well, in order for the notion of position to even make sense, you have to have a certain experimental environment in which you've set up a kind of grid to which you're going to refer the number that you assign the position, okay? So the very concept of position doesn't make sense outside of certain experimental conditions.
Huh.
And similarly, the very concept of momentum doesn't make sense outside of certain experimental conditions. And furthermore, those two sets of experimental conditions are incompatible with each other. You just can't set them both up at the same time. Because, for example, you might have to have a screen that for the one is rigid and nailed down, and for the other one is on springs and can move. And it can't be both, right? And so Bohr's going to say, so you see this Newtonian idea that something could both have position and momentum is kind of incoherent if you understand the concepts this way. You can arrange things so it has a position, and you can arrange things so it has a momentum, as it were, but you can't arrange things at any given time so it has both. Now, you may think that that's interesting or uninteresting or confused, but it's not just instrumentalism, right? And his whole doctrine of complementarity was not just instrumentalism. It was supposed to be this deep neo-Kantian insight, blah, blah, blah. What happens historically is this very obscure and hard to understand Bohrian philosophy kind of dies I think when it comes to the United States, and especially because of World War II, they were too busy building bombs to worry about this. And then it morphs over into shut up and calculate, which is a much more purely instrumentalist view. It says, look, all I care about is that the bomb goes off, right? And I'm also not interested in Bohr, and I'm not interested in complementarity, and I'm not interested in any of that stuff either. I just want the bomb to go off. And then that spirit becomes shut up and calculate. And then that's what kills off discussion of these issues in physics departments. I mean, that's my take on the history.
What I recall from wherever I've heard about the Copenhagen interpretation, sorry for using that word, and what I recall...
No, it's okay for it, because it's not
for this, it's okay.
We didn't like calling theories interpretations, but since Copenhagen isn't a theory, call it whatever you want.
Sure. What I recall is that there is something deeply troubling about maybe this idea that the observer, just by observing something, you have an effect on the world. Does that...
It's not clear to me. I mean, Tim probably has opinions about. Not clear to me that that's part of Bohr's view.
That's more like Wigner. I mean, that's sort of a Wignerian way of trying to spin this thing out. I don't think that's so much the way Bohr was thinking.
Okay. Well, then maybe we should move to an actual theory. And Tim, you've written on this in detail, the Ghirardi-Rimini-Weber spontaneous collapse theory. So how does this react to, I'm guessing it's wave function collapse is what it's...
I mean, and so there's a very easy way to get into this, which is if you look at the kind of the mathematical Bible of the standard presentation, which was written by John von Neumann, he explicitly says, okay, I've got this wave function, and it has two completely different dynamics. He calls them process one and process two. Process two is governed by Schrodinger's equation. It's always linear. It'll give rise to these superpositions, as David was talking about. And process one is a collapse theory, where the wave function does something entirely different. It suddenly jumps indeterministically. The second one is completely deterministic. Schrodinger evolution is completely deterministic. The other part is indeterministic. It's governed by Born's rule for the probabilities. It takes you from a non-eigenstate of a certain operator to an eigenstate. All right, so you can't imagine two evolutions as different as these, right? And then your natural thought is, but when does one happen and when does the other happen? And then you get the unhelpful answer, oh, it collapses when you make a measurement, right? So this is where you get the mess. The GRW approach to this, which is also so simple, it's shocking. I mean, I first heard about this from John Bell in Erice. I'll tell you a little story at the end. But their solution to this was kind of amazingly simple, because if you go that route, if you go the von Neumann route, then what's in front of your mind is, but what's a measurement? But what's a measurement, right? And then maybe Wigner comes and says, oh, you need a conscious mind to register a result to get a measurement. And this is all very central. And what the GRW people did is they said, well, yeah, there are these collapses. What triggers them? Answer, nothing triggers them. Nothing. Not making a measurement, not a conscious mind, not gravity, not anything. They just happen randomly. They happen with a fixed probability per unit time, per particle. There's no trigger, there's nothing like that, but they give you numbers. It happens once every, 10 to the 15th seconds or whatever it is, okay, per particle. And how does it happen? Does it go to an eigenstate? No, it doesn't go to an eigenstate of anything. It happens by multiplying by a Gaussian. They give you a nice mathematical thing. And now you have a mathematical theory with wave collapse that's clean. It doesn't involve any shady notions. When I first learned about this from Bell himself, and I went up to him afterwards, and because of my state of mind, I went up to him and I said, but you mean it just happens, right? Because all my life I'm thinking, oh, it happens when you observe, or, exactly, can a mouse do it? Can a dog do it? Blah, 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 right? And I said to Bell, you mean it just happens? That's it? You're happy with that? And Bell looked at me. He's a wonderful man. He was the nicest man in the world. And he just looked at me and smiled, and he said, you don't appreciate what they've done. And that's all he said. It's all he needed to say. I mean, I didn't have any response at that time. And then it took me a while to absorb what he meant. And what he meant was, they've taken this kind of collapsy idea and gotten rid of all the problematic concepts and replaced them with math, right? With clearly defined mathematical laws. So this is a proposal for real physics. And he was interested in it, and you ought to be interested in it for that reason. Now, it leads to other problems. David had this thing, the Tales of Schrodinger's cat, earlier on in his career, that if you try to ally that dynamics with some other interpretive principles you're used to using, then you get into trouble. And the thing to do is to get rid of those interpretive principles. It took a while to work all that stuff out. And there's a place where an issue about local Beables comes into this, but that would probably take us too far astray. But the main point is that they just wrote down some equations and said, that's the theory. If you want to know what happens, analyze that. And that is an example of what can be done. It's a refutation of the Copenhagen claim, which is basically, you can't understand what's going on. You say, well, I can understand this theory. Maybe that's what's going on.
So another theory, the Everettian theory of quantum mechanics. I can't recall whether it was Hugh Price or David Papineau who I was talking to, but one of them told me, I think, that it's the dominant theory in the UK, but I get the sense that is absolutely not the case here. Yeah, I've definitely heard other people say it's absolutely crazy. And David, I know you've probably both written and thought a lot about it, but what is the Everettian theory?
Well, there is this dichotomy suggested by the discussion we've had so far, that if you want to get measurement, if you want to get the word measurement out of the axioms, two strategies suggest themselves. One, you deny that the standard linear quantum mechanical equations of motion are actually the equations that govern the evolution of the wave function at all times under all circumstances. That's the kind of thing that happens in the GRW collapse theory. Another thing you can do is hang on to those equations of motion, but deny that the wave function is a complete description of the physical system at any given time. That's what's going on in so-called hidden variables or extra variable ways of reconstructing quantum mechanics, like Bohmian mechanics we've discussed. There is this third tradition of, as it were, trying to have one's cake and eat it too. Okay, that is both to assert that the wave function by itself, without any additional variables like in Bohmian mechanics, is a complete description of the world, and unlike in a theory like GRW, to insist that the correct equations of the evolution of the wave function of the universe is this original linear unmutilated Schrodinger equation. Okay, good. You say something's got to give. The measurement problem came from somewhere. The measurement problem, as it were, came from this idea that if we if we hang on to the equations of motion, then what we're going to end up with is a superposition of my brain believing that the experiment came out this way and my brain believing that the experiment came out that way, and so on and so forth. And there are a bunch of suggestions going back to Everett in the 50s to the effect that there might be a way of making sense of this, where you regard the different components of these superpositions, at least once it gets to the level of the macroscopic, or once a process called decoherence has occurred, once something called environmental decoherence, which there's no point in going into here, has occurred. Once you're talking about a superposition of a state of my brain in which I believe that the experiment came out this way, and another state of my brain in which I believe the experiment came out that way, the right way of understanding what's going on there, okay, is that the original single world or my single brain has somehow split into two. One of which actually believes that the experiment came out this way, the other of which actually believes that the experiment came out this other way. There are all kinds of questions about how one would actually try to make sense of a picture like this. Probably the most concrete of those questions, the most extensively discussed of those questions, center around a worry about whether one can still make sense of talk about quantum mechanical probabilities in a case like that. What the theory seems to be saying is that there's definitely going to be a descendant of me once this experiment is over who believes that it came out this way, and there's definitely going to be another descendant of me who believes that the experiment came out that way. This in circumstances where ordinary quantum mechanics tells us that there's a certain probability that the experiment came out this way and a certain other probability that the experiment came out that way, and those being those probabilities are absolutely crucial to the way we tell the story of what our evidence for quantum mechanics is, why we believe in quantum mechanics in the first place, so on and so forth. So there had better be a way of making sense of that probability talk, and there is at least prima facie a tension between the fact that on one hand, this theory is going to be completely deterministic. The wave function evolves in a perfectly deterministic way. There is definitely going to be one of me who believes the experiment came out this way, and another of me who believes that the experiment came out that way. There's a tension between that and this need to talk about probabilities. If I have an amoeba that's about to split into two amoebas, and I ask the amoeba, what do you think the chances are that you're going to end up as the amoeba on the left? Okay, it seems like the right answer for the amoeba to give is, that's a stupid question. There isn't any particular probability that I'm going to end up as the amoeba on the left. There are going to be two amoebas. It's not even clear that it's going to make sense to ask which one is the original amoeba, which one is the one you're talking to now, so on and so forth. So in exactly this way, there's a prima facie worry about whether one can make sense of talk of quantum mechanical probabilities in a picture like this. There's been a huge amount of energy and ingenuity poured into various projects aimed at showing that you can make sense of probability talk in cases like this. I don't think any of those projects pan out. I think Tim probably has similar worries. This leaves aside all kinds of other questions about ontology of this theory and so on and so forth, what we're really supposed to imagine the world looks like on this theory. So the theory faces a whole bunch of challenges. To me, and I suspect to Tim, those challenges look very daunting.
Yeah, that's true. And let me add one more, which I think people don't often talk about. I don't know that I myself have ever mentioned this, but it connects back up to the Schrodinger cat thing and that not being a measurement. That is, even in the description David gave, which is perfectly correct, you help yourself to something that makes it sound more comprehensible than it is, because you kind of focus on cases where you do an experiment that we might call a measurement, where, say, the idea is I have a needle, and at the end either the needle goes this way or goes that way, right? So there's just these two possibilities, and you end up in a superposition, and they say, well, they both happened, right? And it's like quantum mania. It's what parallel worlds, right, that we have in all the movies these days. But in the Schrodinger cat case, it's not that you do something that has only two results, as it were, live cat and dead cat. Because whether the cat dies in Schrodinger's setup, which depends upon whether a particular piece of radioactive material decays over the next hour, can happen at any time over the next hour. And so it's quantum mechanically possible that the cat dies immediately at the beginning of the hour, or a millisecond later, or a nanosecond after that, right? I mean, there's actually, it's not as if the thing branches, as it were, into a live cat piece and a single dead cat piece. There's a single live cat piece, and then a whole continuum of different dead cats that died at different times in different ways that get smeared out, as it were. I mean, this was Schrodinger's worry, that dead cat would be all smeared out all over the cage in kind of weird ways. And he says, that's just ridiculous. That doesn't happen. So even, talking about a finite number of possible outcomes, all of which occur, which is weird enough, because again, you say if they all occur, then they're all actual outcomes. And what do you mean by probability? Even that talk about a finite number is giving yourself more than you are really permitted to have by the theory itself. So there are all kinds of deep conceptual problems about what's going on.
David, this is the last question I'll ask before I know that you have to go. But so you two, or David, you mentioned ontology, but the two of you mentioned that you don't see yourselves doing philosophy of physics. You construe it as, or see it as, foundations of physics. I'm wondering here, though, in particular with many worlds, if this at all interacts with philosophy, particularly David Lewis and possible worlds. I asked this of Joel David Hampkins because he has this set theoretic multiverse view, and he saw no connection whatsoever and doesn't think of it in this way. But I'm wondering if there is any connection here.
I don't see, I'm sure Tim has stuff to say about this too. I don't see a very direct connection with Lewisian talk of possible worlds. To the extent that Everettian talk about multiple worlds is coherent, these are worlds which physically interfere with one another,
Right. Okay.
in principle. So there isn't the kind of, in Lewis, you tend to think of the possible worlds, even if they're all concrete the way Lewis thought of them, as totally causally cut off from one another. In the Everettian case, if it were true and coherent, you could in principle do experiments, measuring interferences between various of these worlds. So, I mean, I know there are I know there's been some recent work, which I'm not very familiar with, sort of trying to turn this on its head and to see what's going on in Everett as the right way to think about modality philosophically. I'm not so familiar with how that works. It's certainly not the way I've thought about this to the extent that I know how to think about Everett coherently at all.
I mean, let me just add one more thing, which is David's perfectly right. The as it were, observable interaction between the worlds would not be acceptable to Lewis. But also what Lewis used to isolate the worlds from each other was spatiotemporal disconnectedness. And even if in the many worlds picture you got a splitting that was so complete that the two resultant worlds didn't interact, they still connect to the same space-time origin, right? They're spatiotemporally interconnected. So these can't be the Lewis's worlds. They just can't be by Lewis's own criterion of what makes a world.
I'm sorry, something I didn't know.
No problem at all. Thank you so much for doing this with me. You're always the best.
Sure. Okay. Thank you.
Yeah.
So one last theory, not interpretation, that I wanted to ask about. So you mentioned earlier in the conversation when we were talking about the Einstein-Podoksky-Rosen argument that this phrase "God does not play dice" is not what motivated this whole paper. But as far as I've been able to gather from the discussions of quantum mechanics that I've listened in on, there is a contingent of people who are deeply troubled by the randomness that seems to be inherent to at least some of the theories of quantum mechanics. And are there any important theories, like maybe is the Bohmian theory might be one of these that tries to give a determinist picture of what's happening?
So the Bohmian thing, again, there's a kind of big umbrella that's called pilot wave theory. And you could say in the pilot wave theory, first of all, you have a wave function. Of course, you have a wave function or a quantum state in all these theories. It never collapses. So this kind of GRW move of actually having physical collapses is off the table. It also means you don't have to worry about describing the collapses because they don't occur. There's really only one wave function in the theory. It's the universal one. There's the kind of master quantum state of everything. And it always evolves linearly. It always evolves by Schrodinger's equation. Now, in order to avoid this many worlds result, the way you avoid it is you say, yeah, but of course, there's some more than that in the theory. There are these other local Beables, like particles or fields or something, that are the familiar things that cats and dogs and mice and tables and chairs are made out of. And in the original Bohmian mechanics or de Broglie-Bohm theory, which is a non-relativistic theory, and it's a particle theory, there are particles. I mean, this extra thing that goes beyond the wave function are particles, and they're really like classical point particles that move around continuously in space in accordance with a certain well-defined deterministic law that's called the guidance equation. The wave function plugs into the guidance equation. So that's why the wave function is guiding the particles. The wave function determines how they move, yes? And does so deterministically. The whole theory is deterministic from beginning to end. When you move on to do what's called quantum field theory, which allows for phenomena that the simple quantum mechanics doesn't. Like in simple quantum mechanics, there's no particle creation and annihilation. You just have a given set of particles. If you have 18, then you always have 18. But in the lab, you see things that are normally described as the creation of new particles, or an electron and a positron coming together and annihilating. So the particle number changes, yeah? So of course, physics has to account for that. And the gadget we have that does that is called quantum field theory. So then you say, well, what would a kind of pilot wave version of quantum field theory look like? And probably the easiest way to do it is actually to go to an indeterministic theory at that point. Or another thing you can do is you have a little bit of trouble that comes from dealing with space-time as a continuum. You can try and make space-time discrete or put it on a lattice. And if you do that, then the natural thing to do is to have some of the theory of how the particles move, become indeterministic and give you the probability at any given moment that it jumps from this lattice point to a nearby lattice point, right? And so most of the people I know who do this stuff professionally, they're fine with that. They say, okay, if the easiest thing and most natural thing to do to implement this master idea is to have a deterministic dynamics for the wave function, but an indeterministic dynamics for the extra stuff, so be it. They're not upset about it. There are a few people who are. There are a few people who really want determinism and would really prefer it, and they might look for other options or, fancify the theory or add something to the theory to try and recover determinism. But I can just report sociologically, almost all the people I know who are attracted to that approach are not attracted because of the determinism. They're attracted because it's a clear theory. You can write it down. It's mathematically simpler than a collapse theory because you don't have collapses. And to many people, the collapses just don't smell right. What can you say? You have the intuition that just seems like odd behavior. So yeah, the determinism part, and there are letters where Einstein clearly states it wasn't the indeterminism that really bothered him, right? It's the non-locality. But in all these theories, you have the non-locality, and the way you make your peace with that is by reading Bell and saying, gosh, I can't get rid of it, right? I mean, like it or lump it, it's there, right? Like it or lump it, the actual experiments violate Bell's inequality. And the only way to get that out of a theory in a clean way is to put some non-locality into the theory. Okay, so let me figure out how to do that in a mathematically precise way, which can be done.
Now I'm thinking back to our last conversation where I don't know what the term is, but you sort of took what I'll call maybe a nomological primitivity to maybe like the direction of time or some things like that. Do you sort of take this idea of non-locality, even though it isn't intuitive, as just something primitive? Is that what you're suggesting?
Well, primitive, I would apply to elements of an ontology. So I think that I'm a primitivist about the direction of time, that I think, yeah, time is a directed kind of thing. It doesn't inherit its direction from anything else. Its direction isn't given by the entropy gradient or something like that. It's just an intrinsically directed thing. There's no further analysis of that because, that's fundamental. That's where my spade is turned, right? And this is the thing every person doing metaphysics or doing ontology has to make decisions about where they're going to stop doing it. This is very much like Goodman's discussion of a philosophical conscience, right? What do you think is acceptable without further explanation, and what do you think is unacceptable without further explanation? And people have different consciences, and there are dangers either way, right? If you're looking for the foundational things and you stop too soon, then you miss some underlying explanation. But if you insist on trying to dig beneath the foundations, well, there's nothing beneath the foundations, and you're never gonna get there. So I would say, yeah, I take the direction of time to be foundational, primitive, not explained in terms of anything else. David would completely disagree. Lots of people would disagree. I take the quantum state to be foundational. I don't think you explain it in terms of anything else. I take a certain space-time structure to be foundational. Exactly what it is up to debate, but it's not explained in terms of anything else. So these are the foundational things. Now, the non-locality is a matter of the nature of the dynamics. So it's in terms of these fundamental things that I'm going to write down a physical theory. And that dynamics, which explains how the things evolve, that's either local or not local. That's not a further, that's just an analytical fact about the nature of the dynamics. And you can do Maxwellian electrodynamics with a completely local theory. And you can do Newtonian mechanics basically with a completely local theory. But neither of those can violate Bell's inequality, and Bell's inequality is in fact violated for these experiments done far away from each other. And so there has to be some real physical influence of what goes on in one lab for what happens in the other lab, even though the other lab is really, 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 really far away, you know.
Mm-hmm.
And in fact, so far away that even light signals couldn't get you from this lab to that lab in time. That's, I mean, I wouldn't say that that's fundamental. It's just inescapable, right? It's just you're not going to be able to write down a physical theory that actually makes the predictions that correspond to what we see without that. That's what Bell proves. Mm-hmm. A local theory can't make those predictions. So I wouldn't use the word fundamental there because it's not a piece of ontology. It's rather an aspect of the dynamics.
Sure. And something we started off with was this disparity between our classical picture of the world and the quantum picture of the world. And I was just trying to think why it is that I find the idea of randomness so concerning. And I think it's because in our classical picture of the world, there isn't any. But you suggested, or at least I inferred from what you were saying, that the indeterminacy doesn't bother you at all. And
no, I mean,
yeah,
I mean,
can you explain why it doesn't? Maybe it
sure.
Doesn't need an explanation.
But I mean, there's some easy things to say, which is having probabilities in many circumstances for everyday life. The relevant probabilities will be either very, 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 very near one or very, 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 very near zero. They won't be exactly one, they won't be exactly zero. But if they're close enough, okay, close enough, you know, close enough is good enough. You know, if quantum mechanics tells me if I drop my plate on the table, there's some chance it'll quantum tunnel through and hit the floor. But that chance is so small that you could be dropping plates on tables for the entire history of the universe and not come near any noticeable chance of that happening. Okay, you know, I mean, certainly that doesn't bother me. If subatomic things happen with really, you know, comparable probabilities, okay, there's a 25% chance of this and a 10% chance of that. So big probabilities, but there are microscopic events going on. Again, okay, but I interacted with the world at a macroscopic scale. It's not clear to me. So I'm not sure, am I supposed to be upset just about the very idea of probability or of indeterminism? All I can report is that I'm not. I'm not sure why I should be upset about it. Maybe you could articulate, I mean, you could just feel creepy about it, I guess.
Yeah.
I personally don't feel creepy about it. So if you could motivate why I should be upset about it, I could better answer the question. I just can report subjectively. Yeah, okay, maybe it's like that.
Yeah, I think it is just a creepy feeling.
Okay.
Really.
Yeah, I'm not an exorcist, so I can't.
Sure. Well, I'm sure that if I had the training in physics that you have, that might be dispelled because I wouldn't be committed to viewing the world in this sort of classical way.
Yeah, I mean, and classical is kind of a funny word. You know, Democritus had this picture of these atoms falling through empty space, which I don't know whether you want to call it classical. It's certainly very comprehensible. And he was stuck with this problem. He said, but then why don't they just always fall? I mean, why? They're supposed to start banging into each other and connecting up and making things. And so we put these indeterministic swerves in, right? Just to solve the problem. Okay, sometimes they just do. I don't know. Should I be really upset about that? I mean, the world's the way the world is. I can't let my prejudices, if I got a prejudice toward determinism by learning Newtonian mechanics, well, Newtonian mechanics is wrong. We know that. If I got a prejudice toward determinism by learning, Maxwellian electrodynamics, but that theory is false. I should not let the familiarity of a bunch of false theories that I learn prejudice me or close my mind to the true theory.
Right.
Right.
And if I were really committed to just my experience, then I would also have to disavow all speech of electrons and quarks and all of these things that I can't observe that are equally, I guess, unintuitive.
Yeah. And look, your everyday experience, you actually appeal to things like luck and chance.
Yeah.
You say, look, that was just a coincidence, or that was just by. I mean, Aristotle talking about luck and chance as kind of agents. I mean, he's upset of talking to them as agents, but it's not that unintuitive to say, yeah, some things are determined, and some things, sometimes it comes out this way, and sometimes it comes out that way, right? I try and make a nice crepe, and sometimes it comes out okay, and sometimes it doesn't. In everyday life, it's not clear that the notion of chance, fundamental chance, is that foreign to everyday thinking. It kind of gets driven out of us if we do a lot of physics, because we start with Newtonian mechanics and everything, and those are deterministic theories.
Just a quick clarificatory point before we move on a little bit. Is quantum field theory then, which arose, as you mentioned, at least in part, because of this annihilation and creation of particles, is it the successor theory to quantum mechanics, in the sense that are people not doing quantum mechanics anymore? Quantum field theory replaced it?
Yeah, I mean, but by the kind of, I'm not sure that people are very strict about how they use these words.
Okay.
Quantum mechanics usually means a non-relativistic particle theory.
Okay.
Where there's a fixed number of particles. As soon as you move to a relativistic theory, I don't think you should officially call it quantum mechanics anymore. And certainly when the particle number becomes variable, you use a bunch of mathematical objects that everybody would associate with the thing we call quantum field theory. Now, whether quantum field theory really postulates fields, that's a different matter. I mean, it's just a word. But certainly quantum field theory has aspects, and it has problematic aspects. I mean, you may have heard that there are these problems of renormalization, because in quantum field theory, unlike in regular quantum mechanics, there are techniques for doing calculations, and what they do is they give you infinity all the time. And you might say, well, that's sort of problematic, right?
Yeah.
I can't do much with infinities. And then there's a whole struggle to bring these things under control by what's called renormalization theory. I mean, and there's a lot of actually even philosophical literature on this. So there are definite, very noticeable technical mathematical changes from the thing we call quantum mechanics that you would learn in a book which has the title Quantum Mechanics, and the thing we call quantum field theory, which you'd only learn later in your career if you're studying physics.
And then I'm wondering where the philosophical term or landscape of realism fits into what we've been discussing. I take it, since these are theories and not interpretations, I mean, whatever theory you accept, you're a realist about the ontology it postulates. But then David mentioned that Bohr was an instrumentalist, and I don't think of being an instrumentalist as being a realist. So I'm wondering if there is more complexity.
Yeah, I don't think that's a correct reading of Bohr. I mean, I think to understand Bohr, you first have to understand that he was brought up in place where there's a lot of neo-Kantianism, and actually a lot of what he says is through the lens of Kant in weird ways that no normal physicist nowadays would even have an inkling what was motivating Bohr to say some of the stuff he said, because he had this philosophical background in neo-Kantianism. And I'll just say how I use words. I think a physical theory makes definite postulates about its ontology. Now you say, are you realist about that? Well, I don't know what you mean. Yeah, they're just definite postulates about what really exists. I don't see how you can do physics and not be doing that. Then there's a question, which is the question I call scientific realism, which is an epistemic question. It goes, okay, I have this theory, it makes definite postulates. Say this one says there are particles, this one says there are no particles. Okay, they're different theories. Can the empirical data I have, plus maybe other principles of rationality, make it reasonable to believe, that is, to put a fairly high subjective credence on one of these and against the other one, right? And to that extent, I'm a scientific realist, because I think, well, yeah, sometimes it can. I think there are electrons. I think there are quarks. I think, we've worked out that there are, superclusters of galaxies and all kinds of things, that there are evidence for them is so strong. It's not to say it's absolutely probative and maybe this whole thing will be overthrown, but that a rational person should be happy to say, I believe there are electrons. To that extent, I'm a scientific realist. Now, I don't know. We may well end up with different candidate fundamental physical theories that are different theories because they make different postulates about what exists and how it behaves, that cannot be distinguished experimentally. And there are no other even kind of plausible rational principles to say this one's much more plausible than that one. In which case I'd say, well, in that case, you shouldn't make up your mind, right? You shouldn't have a strong bias to thinking this one's right and that one's wrong, because the evidence just isn't strong enough to do that. As a scientific realist, I think sometimes the evidence is strong enough to do that, but I'm not committed to saying always it is. That depends on how things play out.
Well, something that I wanted to finish on was going back to entanglement and non-locality, and two views of this that have come up in some of the discussions I've had on the podcast. So one is, I spoke with Jonathan Schaffer of Rutgers, and I think he worked on a paper that touched on entanglement with Jinan Ishmael, and his belief that the cosmos is the one fundamental entity he thinks sort of can account for entanglement, how, at least on some level, how two things so far apart can interact with one another instantaneously. It's because they're not fundamentally two things. They're still one thing. They're part of the cosmos that is the one thing. And I might have not given the most charitable description of his view because it's not my view and I can't reconstruct it perfectly. But are you familiar at all with this argument? And I'm curious about how it...
Okay, so let me break down some things here. First point, as I've said, I think there just is non-locality because the experiments tell us there is. Second question, okay, but how do I implement that in the physics? I mean, I need the physics to give me, the right predictions, and I need some non-locality to do that. In quantum mechanics, there is a very tight connection between a system of particles, say separated particles, being able to predicting you'll can violate Bell's inequality, and whether the quantum state of that pair of particles is entangled or not, which is a perfectly well-defined thing. Sometimes it's entangled, sometimes it's not. It's called a product state. product states, if they're in a product state, they can't violate the Bell inequalities, or you will not predict they'll violate the Bell inequalities. If they're an entangled state, you can. So there is a very deep connection in that theory between non-locality and entanglement. Of course, maybe all of quantum mechanics is wrong. Maybe this whole talk about wave functions will be replaced by something else. Whatever it's replaced by will have some sort of non-locality in it, I claim, because it has to. Maybe it will have nothing to do with entanglement. Maybe the notion of entanglement won't even make sense in this new theory. So the connection is very tight within the bounds of quantum theory, but it's not that tight at a more general level. Now, one thing you want to say, and I said this before, ultimately you want to say from an ontological point of view, there's a quantum state. The quantum mechanical wave function is describing something physical. And ultimately there should really only be one of it, which is the one for the entire universe. And it's going to be massively entangled if you try and describe it in terms of different systems. This thing will be massively entangled. And so the idea that there is this one fundamental, unified, global, universal thing is a natural way to go. Now, you then have the question, okay, that's true for the quantum state, but is there stuff other than the quantum state? Now we're back to the question, is it a monistic theory that only has one thing, or does it have, in a pilot wave theory, there's the quantum state, but then there are these particles or whatever that are being guided by the, they're different. They're not entangled. I mean, they are just separate. They just move around in space in a very classical, your classical picture of them is correct. So you can believe that fundamentally there is a universal quantum state that is metaphysically extremely important, ontologically extremely important, but say that doesn't exhaust all there is. So I'm not a monist in that sense. I think in addition, there are these local Beables, and they're something different. I think that's actually the right way to go. And as I understand it, Jonathan really wants monism. He wants there to be only one fundamental thing. In the picture I have, there's more than one fundamental thing, right? One of those things has this kind of fundamentally global character, and that's the one associated with the wave function because of entanglement. And that's the one I will appeal to explain violations of Bell's inequality, the role that it's playing. But I'm not a monist in thinking, like, I don't know, Spinoza or, I think there's more than one fundamental ontological category.
And then maybe you've said all you want to say on this, but I also recently spoke with Hugh Price, and I asked him, what I said to him was that I often hear time mentioned in conjunction with relativity, but at least in the popular discourses on the philosophy of physics that I pay attention to, like Sean Carroll's Mindscape, for instance, and maybe I'm just missing it, but I don't often hear time discussed as problematic in relation to quantum mechanics. And he brought up a way that time does for him play an important role in quantum mechanics, and it again relates to entanglement. And what he suggested, and I think he has a piece that just came out today on it, I saw briefly on Twitter, but it's that we can account or might be able to account for entanglement by employing the notion of retrocausality, so backward causation. And when we so I don't really know how to say it properly with the physics jargon, but when we interact with one particle and it, for lack of the right words, fixes or affects the state of another one simultaneously, we can account for this by thinking of the first particle as sending information backward in time to the point where these two particles first interacted. Have you heard of this or thought of that? Or
everything you're just describing, you could read in many places.
Okay. Did I describe it okay for my audience?
You described what you would read in a perfectly adequate way.
Oh, perfect.
I don't think you can make any sense of it. I just literally don't think you can make sense of something going backward in time, or I mean, I think causes precede their effects, precede them in time. And that's, what makes them the causes, and the other things, the effects. But the idea of something traveling backward in time in this sense, I don't think actually you can make any sense of it. Certainly you don't want to, the way time and time direction play into quantum theory is very sensitive to what version of quantum theory or which of these particular theories you're talking about. The Schrödinger equation is time reversible. So from the present state, given that equation, I can both completely predict the future and retrodict the past by more or less the same mathematical considerations. In a spontaneous collapse theory like GRW, that's just not true, because the collapses actually, as it were, go in a preferred direction of time. There are no uncollapses that if you just looked at the wave function and what it does according to that theory, you could say, oh, that's the future direction, I see. So those are two things that would be called quantum theories, and their relation to the direction of time is entirely opposite. I personally don't think, I actually don't think this talk about time reversibility, I don't think even that's good terminology. What you really have is a velocity reversal symmetry, but that doesn't imply there's no direction of time. But what I just said, many people will disagree with, and I will disagree with them. It's a long story about whether there's a problem of direction of time, and if there's a problem, what it is, and what its solution would be. Sean certainly would disagree with me about the direction of time. I know for sure. What he would say about it has nothing to do with retrocausation. It has nothing to do with the sort of thing that Hugh's talking about, right? And you have a bunch of moving pieces here. You have the notion of causation. You have the notion of cause and effect. You have this phrase, something going backward in time, whatever the heck that's supposed to mean. Am I going backward in time right now? Why not? I mean, am I going forward in time right now? I mean, I think I am, because I think time itself is going forward. And, but this is a whole mare's nest of conceptual and philosophical issues that are all interconnected in very complicated ways. And I can't say anything dispositive about it that would be comprehensible. But the way you describe people talking about it, yes, that's the way they talk about it. I'm going to solve this problem of non-locality by having causes that go back in time. Right? There's no causes that go this way. They go this way and then that way. Right? That's what you just described.
Yeah, exactly.
I actually think that's not even quantum mechanics, because quantum mechanics, let me say why. Quantum mechanics would say the universe could have started out in an entangled state. Okay? So I do these two experiments right after the Big Bang, or right after the beginning of the universe. Experiment here, experiment here. It's in an entangled state. You violate Bell's inequality. Nothing could go back and come back forward, because there's no back to go to, because I just started the universe. That's perfectly possible quantum mechanically. Perfectly possible. Nothing would rule that out. So if your theory needs that backward, forward, zigzaggy thing, no guarantee you're even going to have it. And quantum mechanics doesn't work that way anyway. You don't calculate backward and then forward and then backward and then forward. You always calculate forward. The equations are just solved in one direction. You don't do any zigzaggy stuff. Yeah. It's just not the way it works. And it's very hard mathematically to even understand how to solve a theory that would have equations that work like that.
Right. Okay, well, that was all immensely helpful, as it always is. I'll finish with one last question. David alluded earlier, I think, that some of the limitations in the theory development the theory development is constrained by technological limitations. And on a speculative level, are there any, or maybe just one might come to mind, deep problems in the philosophy of, or I'll say foundations of quantum mechanics that might be resolved with an unlimited budget? Like, can you think of an experiment
Sure.
that you'd like? Oh, perfect.
Yeah, I mean, look, we're getting David a little bit overemphasized. I mean, he was talking about the fact that the spontaneous collapse theory, the GRW theory, makes slightly different predictions than a non-collapse theory. And how different those predictions are depend upon how you fix certain parameters that have to be put into the collapse theory. But those are actually testable, and there are people who are doing those tests. I mean, there's experiments going on as we speak in Gran Sasso in Italy, deep underground, that bear on that question. And people have been doing those experiments for 20 years at least. And they keep putting pressure. That is, if there were these collapses, you would expect you could see evidence of them, and they've never seen the evidence. Now, at this point, you can still readjust the parameters and kind of hide, you keep ruling out regions of parameter space empirically. Probably in 10 years, it'll be ruled out. And if you put $1 billion into it, they would do it a lot faster, but there's not much money. I mean, in fact, these experiments are often piggybacked on other experiments that get funding. This is not the kind of thing that gets funded. But ruling out a GRW type of collapse theory or ruling it in. I mean, I don't want to say my guess is it'll be ruled out, but it could be ruled in by noticing systematic deviations from standard quantum mechanical predictions. Yeah, that's going on now. It's hard. You have to be clever. You have to know what to look for, and you have to look hard for it.
Is the experiment something that can be easily described, or is that too much?
I mean, one thing that happens in a collapse theory, spontaneous collapse theory, I have a wave function that say kind of in your head, think of it as spread out in space. And what the collapse does is it localizes it. So it all of a sudden snaps, not perfectly localized, but to a very, very narrow bell curve, kind of like this, right? So you go from way spread out to this. Now, this state, the narrow one, has a lot more energy in it by standard quantum mechanical principles than the spread out one did. And that energy can show up by releasing a very high radiation, like a gamma ray or something, that you don't expect, but these would be spontaneously produced at a certain rate. And so if you monitor certain materials, I think they're using gallium, I'm not quite sure. You monitor certain materials and you say, if there were these spontaneous radiation or spontaneous heating up, you would see it. This is the same kind of thing. When I was young, they were looking for proton decay. And they had theories that predicted proton decay, but they were very rare. And you had these huge, huge things of water, perfectly filtered water, and all these photodetectors looking for these characteristic radiation that would happen if a proton decayed. And it was so rare that it was going to take decades to check, and they never found it, right? And it just took a long time for the data to come in, and then there's, to this day, no evidence of proton decay. This is very similar. Phenomena you would get from collapses that you don't get without collapses, but they're rare, and you have to look in good places to look for them.
Well, Tim, and then David in spirit, thanks again so much for doing this with me. Again, you're such a good teacher, and thanks for your patience. Hold on, Geeslings. Before you go, please like, subscribe, follow if you haven't already. Smash all those buttons. And also, if you haven't followed me on Twitter at Robinson Earhart, or if you're not joining me every morning as I eat my pint of ice cream on Twitch at Robinson Earhart on Robinson Eats, please do so.